All right, good morning, everyone. We're going to go into the periodic table of elements, and we want to just take a little time to look at some of the foundations and then move through as time allows. Take your time as we go through, even if it seems like I'm rushing a little bit. Feel free to pause, to rewind, and to make sure you have all the information. Now, when we're talking about the different properties of the elements and looking towards preparing you for bonding, one of the things we have to look at is what are the properties of the periodic table and how does that affect the type of bond that you're going to have and so forth. So, starting off with some of the basics. I'm going to start off with our good buddy Mendeleev, or Mendeleev. In 1869, Dmitry Mendeleev actually created the first accepted version. Now, just notice I said that it's the accepted version, not the first version ever. Now, he grouped the elements according to atomic mass and some of the other properties that he found at the time. But one of the things that he did is he actually left some blank spaces because he knew that there were elements that had those properties, but they just hadn't been discovered yet. Here's a diagram or a picture of the periodic table as Mendeleev saw it. You notice these spots where there are question marks. He knew that there was something supposed to be there between these lists, but he just wasn't sure where. Now, as we moved in a little bit further into through the 1800s, I believe the early 1900s, we moved to what we now call this is our accepted periodic table of elements. Now, what's the difference between the two? The big difference that's noted here is still according to the properties between the families, but instead of the atomic mass, now we're looking at it in terms of atomic number, which is actually going to make a little bit of a difference in how we proceed. Looking at the number of protons and increasing. Now, one of the things that you'll note is there are some situations where there's a difference in the atomic number and the atomic mass, or should I say the order. Looking here at cobalt. Cobalt has an atomic mass of 58.93, and yet it's ahead of 58 nickel, which has 58.69, and it's all because looking at the number of protons. Remember, our atomic number again is our number of protons. I tried to make a number symbol. Sorry guys, it didn't work, but we'll keep moving. Now, this is basically organizing the elements in a way that allows us to be able to gather a lot of information. One way that I can sort of put it is when I spoke with one teacher, what he tells the students is, as using the periodic table, one of the big things he's going to do during the year is to teach you how to cheat using this one table. There's a wealth of information there, and so it's just a matter of being able to go in and find what you need and then use it. Once you can understand how it's organized, it'll be a gold mine for you. Now, of course, these are some of the common elements, names, and symbols that you're going to run into. Note a couple of them that a lot of people tend to get wrong a lot. Things like sodium, a lot of people are looking for S, which is actually sulfur, or chlorine, I get a lot of people say Ci, gold, Au, silver, Ag, and so forth. Make sure that you're paying attention to what element you're looking for, because remember, your periodic table that you get for the AP exam only has the symbols. It does not have the names, so you have to have them in your head already and be able to know approximately where they are. Now, when we look at the periodic table, it's divided into three main categories. We have nonmetals, metals, and metalloids. Paying attention to the chart here, you notice that the majority of the periodic table is actually made up of different metals. So we're going to continue to use those when we talk about ionic bonding. All ionic bonding, is actually going to have a metal involved in some way, shape, or form. Now, on the top right-hand corner, this is where we run into our nonmetals. This is going to be our gases and many of our brittle or softer materials that are not found, that do not have these metallic properties. And in between, we get our nice group of our metalloids, which are going to have properties of both the metals and the nonmetals. But let's get into what some of those properties actually are. Now, metals. Metals are going to be good conductors of electricity and heat. They're shiny. They're ductile, which means we can pull them into thin wires. They're malleable, which means we can pound them into sheets, think aluminum foil. And when they react with water and some acids, they corrode or they break down. These are some of the basics that you can sort of just keep in mind how we tend to run with them. Now, what about nonmetals? If we look at nonmetals on the other side, these are going to be not so good conductors, very poor conductors actually. They're not ductile or malleable. They actually break very easily. They're dull. Most are not shiny at all, and many of the nonmetals are actually going to be gases. Not all of them, but many of them will be gases. So you can see that it'll be a little difficult to run an electrical current or transfer heat through a gas. Now, what about metalloids? Now, the name metalloid, of course, meaning metal-like. So it's going to have some properties of metals and of nonmetals. So some will be shiny, some will be dull. Some conduct heat and electricity better than others, better than nonmetals, sorry, but not as well as metals. And many of them are malleable and ductile, while some are not. You want to just keep in mind, think about the things in your cell phone. We always say that your phone is and your computers are always full of silicon, the chips that they make. They make the processors and different things out of. This is going to be very, very light. It's going to be very flexible, but it's also going to conduct electricity and information very, very quickly. And this is why it's used, because of those properties. Now, when we look at the periodic table, we have to look at it in a couple of ways. One, we want to look at what happens in the families or the groups. The groups are going to be the columns. So this will be group 1, and we're going to talk about what the properties are of each individual group, because each one has some specific properties that you want to pay attention to. Now, if these are the groups, as we look going across from left to right, the other thing we pay attention to, these are called our periods. So our periodic table, get it? Periods. Okay, now elements in a period will not have similar properties. Many times not at all. They won't have any properties in common. Going from all the way over here to metals to non-metals, you get a very, very wide range of variety. And so we're just looking at that in terms of the well, we're actually able to see some different trends, which we'll get into a little bit later. We'll talk about the trends when we talk about electron configuration and so forth. So just keep that in mind. Now, these families or groups are going to have similar but not identical properties. Now, if I take the group 1 elements, if you look at the periodic table, if you have one, the one in your planner, or you have one that you may have printed out, if you look at the group 1 elements, that's going to be the ones all the way to the left. You have elements like lithium, sodium, and potassium, and francium, all these different things. Now, each of these have the same characteristics, being soft, very light, almost white, shiny metals. When I say soft, I mean they're soft enough where I could take a butter knife and literally just cut a piece, slice a piece right off of it. Now, what are some other things that we're going to pay attention to in that? We'll get to that in a second. That's where the fun stuff comes in. Now, all the elements in a family will have the same number of valence electrons. Now, this word valence is what's going to tell us the number of electrons on the outer ring, or the furthest out from the nucleus. These are the ones that are going to participate in bonding. And so we'll need to be able to calculate and find out how many valence electrons there are. We can do this by looking at the periodic table and looking at which groups are actually there. Now, the periods are the horizontal rows again, and they're not alike in properties. The first element is always an active solid, and the last one is always an inactive gas, because we start with the alkali metals and we move all the way over to the noble gases, which you may have some experience with. Now, alkali metals, we're going to go through some of the families, but I'll move quick. The PowerPoint will be on Moodle, so if you ever want to go back and read over some of the things that I did not cover specifically, you may feel free to do that. Now, first group that we're dealing with, alkali metals, is going to be found first column all the way to the left, as you see here, and they all have a single electron in their valence electron shell. So when I look at group 1, I can always say, okay, there's one valence electron. Because of that, and because they're metals, they're going to go through what we call oxidation. They're going to lose an electron. Now, they have about the consistency of clay, and they're very, very soft. You can cut them with a knife. Now, the fun stuff, and I wasn't able to put the video up I wanted to, but these are going to be the most reactive metals. When you put them in water, when you put them, even if you leave them out in air, they react very quickly. But if you put them in water, it's actually kind of fun to watch. I'll probably include a link in the information so that you can go and watch what happens when you actually put sodium in water. It's actually pretty nice to see. But because of this reactivity, it's never going to be found free in nature. It's always going to be bonded with something because of that reactive nature about it. Now, moving into our next group, we have what we call the alkaline earth metals. These are the second group. So this is the group 2, or the one second from the left. Now, these also are never found uncombined in nature, and they're going to have 2 valence electrons. Now, we should start to see a little bit of a pattern here for at least these first 2 groups. Group 1, 1 valence electron. Group 2, 2 valence electrons. All of them have 2 valence electrons. Now, some examples include magnesium, calcium, looking down the list, beryllium, and so forth. Now, moving along, we're going to talk about the transition metals. And now, if you look at most newer periodic tables, you notice that they have them in the groups and they say B over the top. These B elements are this way because they tend to change up. They don't follow the same properties as group 1 and group 2 have thus far. So, these elements are the ones we are most familiar with a lot of the times. The examples given here: copper, tin, zinc, nickel, gold, silver. These all fit into the realm of transition metals or type 2 metals. Now, why are they called transition? Whenever we think transition, we think change. If I'm in a transition between jobs, I'm changing jobs, or I may be changing fields, or I'm just making a transition through the building. I may be passing through the halls and things are likely to change. They're usually going to be very, very good conductors of electricity and heat. But again, the properties are going to vary a lot between melting point and the number of valence electrons. The oxidation states will sort of change. So we'll talk about that a little bit more in class, so don't worry. Now, the compounds that are used or that are formed from transition metals are the ones that, like the example given to you here, you're going to see it in paints. Because of those wide range of properties, it's going to allow them to be used to do so many different things, so many beautiful things that you see around you. Now, we want to go ahead and look a little bit further, and now we're going to get into another couple of sets where we can find a regular pattern that we can use. I'm just going to pass by this one, but we're gonna come back to that. Now, the halogens, the halogen family. We're looking at the elements. We've gone all the way to the other end, the second group from the right now. These are going to be the most active non-metals that we deal with. And again, some examples: fluorine, chlorine, bromine, iodine, astatine. These all fit into the halogens. These are situations where these elements have 7 valence electrons. Now, the one thing, I'll come back to that in a second. The big thing that we're going to have to come back to is the octet rule and how these elements work together to make sure that they fulfill the octet rule. But because they only have 7 valence electrons, they're going to do everything they can to become stable. And so they're going to be very, very reactive, especially when it comes to metals, or even some of them we'll talk about are form diatomic molecules. Now, our last group that we're going to cover at this time, and we'll come back and we'll sort of pitch in some of the things for the others, are the noble gases. These are the ones that most of us have heard of all throughout elementary school and middle school. Why are these important? These are the gases that are unreactive, mostly unreactive, I'll say. One important property is their inactivity. Because the outer layer is full. Remember I talked about the octet rule. These have 8 electrons in their valence shell. Since they have those 8 valence electrons, they're not concerned with bonding or making any type of reaction with other elements, as the rest of them are. The goal of most of the other elements, all the other elements, is basically to be like this group. So as we continue to study the periodic table, we're going to look at some of these things and just, sort of ask a couple questions and make sure that we understand what's going on at each step of the journey. Please feel free to ask questions. If something in here did not make sense, please, 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 please ask the question. I will talk to you tomorrow in class. You have a great day, and keep studying.